Hello, welcome back to Learn Physics. In today's topic, we are continuing with our electric charges and fields. Yesterday, we already learned about the dipole and electric dipole moment, torque acting on the electric dipole. Okay, in a uniform field and in the non-uniform field we discussed. Right, so some homework questions were there, so we will go through that first one was define electric dipole moment and its SI unit. Electric dipole moment P equals Q into 2A. Right, so it is the product of one of the charges and the perpendicular distance between the two charges, and the distance between, not perpendicular distance between the two charges, that is called a electric dipole moment. Okay, electric dipole moment is the product of charge and one of the charges and the distance between the two charges. What is its unit? What is the unit of Q? P is equal to Q into 2A, right? So P equals Q into 2A. It's a vector quantity. P equals Q into 2A. So Coulomb, A is meter. So unit is Coulomb meter. Next is, in which orientation dipole in a uniform field is in stable and in unstable equilibrium. Stable equilibrium when it will be, say, torque tau equals P cross E. It will be in stable equilibrium when theta equals 0. If theta equals 0 and theta equals 180, tau will be equal to 0. Right, but when theta equals 0, we can say it will be in stable equilibrium, and theta equals 180 degree, we will say it is an unstable equilibrium. Okay, so now the next question. An electric dipole with a dipole moment 4 into 10 to the power minus 9 Coulomb meter is aligned at 30 degree with the direction of a uniform electric field of magnitude 5 into 10 to the power 4 Newton per Coulomb. Calculate the magnitude of the torque acting on the dipole. So everything is given. It's a direct question. So dipole moment P equals 4 into 10 to the power minus 9 Coulomb, and it is aligned at 30 degree with the direction of uniform electric field of magnitude 5 into 10 to the power 4 Newton per Coulomb. Calculate the magnitude of torque. Torque equals P cross E, or we can write it as PE sin theta. So P is 4 into 10 to the power minus 9 into 5 into 10 to the power 4 into sin 30. Sin 30 is 1 by 2. So 2 into 10 to the 2 5s are 10. 10 into 10 to the power minus 9 into 10 to the power 4. So we will get the final answer as 10 to the power minus 4. What is the unit? It is Newton meter. Okay, clear? Easy questions, right? So next, today's portion. Now today we are going to study about the continuous distribution of charge. Next is continuous distribution of charge. See how we can find out the continuous distribution of charge. See we already learned about the point charges, Q1, Q2, Q3, like that. Many point charges we considered. Instead of that, if I want to consider about one line, see a rod, a small rod I need to find out. What will be the charge in that rod? Or if I want to find out the charge on the surface of the sheet. Okay, or what will be the charge which is present inside and outside? See, in a three-dimensional way, not in a cube. So drawing the sphere in a three-dimensional way, it is difficult for me, so I don't know to draw. Okay, so in this volume, what will be the L? What will be the charge distribution? How we can find out? Here and all we can't consider it as point charges, right? So if it is a line element, we will find out the linear charge density. Okay, linear charge density we will find out. In the case of surface, we will find out surface charge density. Charge density. And here in this case of volume, volume charge density. Okay, clear? So it is linear charge density, this is surface charge density, this is volume charge density. Linear charge density means through a line. Okay, charges are distributed through the line, continuous distribution of charges. Here charges are not point charges, many charges are distributed through this line. Same way on this surface also many charges are distributed, and in this volume also many charges are distributed. So in those cases how we will find out the charge? Okay, linear charge density is represented by lambda. Lambda will be equal to delta Q divided by delta L. Okay, surface charge density, that is sigma, will be equal to delta Q divided by delta S. Okay, volume charge density, rho, will be equal to delta Q divided by delta V. Okay, clear? This is continuous distribution of charge. Always we can't consider the charges as point charges. If charges distributed on the surface, then we should consider the surface charge density. If charges are distributed in on a rod, then we should consider the linear charge density. If the charge is distributed in particular volume, then we should consider the volume charge density instead of considering it as a point charge. Clear? What is the importance of this continuous distribution of charge? So next we are going to study about very important thing, that is Gauss law. Okay. Next is Gauss law in electrostatics. What is Gauss law? See here, Gauss law states that the total electric flux over a closed surface is equal to 1 by epsilon 0 times charge enclosed by the surface. Okay, this is Gauss law. Total electric flux over a closed surface, that is very important. In a closed surface, if I am considering electric flux, see here, now this is a closed surface. This electric flux in this surface will be equal to 1 by epsilon 0 times charge enclosed by the surface. How much of charge is there inside the surface? So that will be equal to 1 by epsilon 0 times charge enclosed by the surface will be equal to the flux over a closed surface. See, suppose if I am finding out the electric flux in a particular surface, electric flux if I am considering, suppose if I am considering electric flux in the surface, now how many number of electric field lines are coming outside? That will show the electric flux, right? So electric flux will be phi is equal to E dot ds. It is always perpendicular. We will be telling the surface will be always, surface integral will always be perpendicular to each other. Already we learned about the electric flux, right? So it is perpendicular like this. See, if I am keeping it like this, perpendicular to the surface, okay, not perpendicular to us, perpendicular to the surface. Electric flux will be always considering surface will be surface area will be perpendicular to this surface. Okay, so we already phi is equal to E dot ds. Here we are considering electric field and the ds. plus q we know it is moving outwards, right, and radially outwards. And ds, what will be the direction of ds? Always perpendicular to the surface. Okay, if I am considering it like this, it will be perpendicular to like this. Okay, if I am considering it in a slanting way, perpendicular to that slanting position. Okay, that is electric flux. So this is about Gauss law. It's very important. It is total flux, electric flux over a closed surface is equal to 1 by epsilon 0 times the charge enclosed by the surface. So now we are going to give a proof for this Gauss law. So proof. I am considering a sphere. In that, a charge is situated at the center. Okay, I am considering, see, this is electric field is acting radially outwards. Okay, so this surface I am considering over here. Okay, here on the surface, not projected, here on the surface I am considering a sphere, considering a point distribution of charge. Okay, so I am considering the flux enclosed in the surface. Okay, so small surface ds I will consider first. After that I will find out the total electric flux. Okay, so before that we should write down how we can represent the flux over a closed surface. Flux means we know it is E dot ds. Right, so closed surface means closed integral. It is, we are adding all the small surfaces in a closed surface. So closed integral E dot ds is equal to 1 by epsilon 0 times q charges there inside means q. How many charges are there? If q1, q2, q3, q4 are there inside means we will add up everything. Okay, so this is the representation of Gauss law. Okay, closed integral E dot ds is equal to q by epsilon 0. Okay, so here we are going to prove that. Okay, now what will be the electric field in that region? E will be equal to 1 by 4 pi epsilon 0 q by r square. Right, then dot ds. So now E dot ds we should find out. E dot ds. E dot ds is equal to 1 by 4 pi epsilon 0 q by r square into vector r. It's a vector, right? Into vector r dot. What is ds here? ds will be equal to 4 pi r square. 4 pi r square is the surface area of the sphere. Okay, 4 pi r square into unit vector n. N will be acting perpendicular to the surface. Right, it is acting perpendicular to the surface. E will be acting like this. Here 4 pi r square r dot n. What is r dot n? R dot n will be equal to 1. What is the reason? A dot b? AB cos theta. Right, so what will be this theta between them? Cos 0 is 1. So r dot n is equal to r n cos 0. R and n are unit vector. So 1 into 1 into 1, we will get the final answer as 1. Clear? So here we will get what is the remaining thing? That is equal to q by epsilon 0. So closed integral E dot ds q by is equal to q by epsilon 0. Clear? So here how we are giving a proof for this Gauss theorem. First we are considering a sphere having radius r. A charge q is placed inside on the center of the charge, and ds is the surface charge element. Okay, then here electric field will be acting radially outwards, and to the surface area it will be always perpendicular to the surface. So E equals 1 by 4 pi epsilon 0 q by r square. We already learned in the previous session. If you didn't watch that video, please go through the description box. All the videos related to this chapter is given there. Okay, so 1 by 4 pi epsilon 0 q by r square into r. So closed integral E dot ds will be equal to, instead of E what we can write, 1 by 4 pi epsilon 0 q by r square. What is closed integral ds? 4 pi r square into n. 4 pi r square will get cancelled. We will get the answer as q by epsilon 0. So this is a proof for this Gauss law. So here we should understand that, see, in a Gauss law we will be applying for a closed surface. Suppose if we are considering a surface which is not closed, then how we can find out the surface and how we can apply the Gauss law over there? We should consider a closed Gaussian surface over there. We can imagine, see, a closed Gaussian surface. So first step is we should imagine a Gaussian surface. Okay, and always we should consider about this charges as enclosed charges only we should consider. Okay, the charges which is covered inside the surface, inside the Gaussian surface. How much of charges are there? That charges alone will be included over here. Okay, and E dot ds, while we are considering E dot ds, E will be acting normally and ds will be acting normally. So R dot n, this will be equal to 1. So no need to take the angle between E and ds. E dot ds we can consider it as E into ds. Okay. And this Gauss law is applicable for the charges which are symmetrically distributed. So one symmetry should be there. If the symmetrical distribution is not there, we can't consider this Gauss law. What is meant by symmetrical distribution? Say if it is a charged conductor, then we can say charges will be symmetrically distributed inside that. Okay, it's equally distributed. Some plus q over here, some plus q over here, plus q over here, and 5q over here. That one we can't consider. Everywhere it should be symmetrically distributed. Then only we can find out the in the case of Gauss. We can use Gauss law. And this Gauss law has a dependency of 1 by r square dependence. That because Gauss law is depending on E. So E is inversely proportional to r square. So inverse square dependence is there for Gauss law also. Okay, clear? So from this Gauss law we can prove this Coulomb's law. Okay, so these are the two main laws which are studying in the first chapter. So here Gauss law we already learned total electric flux over a closed surface is equal to 1 by epsilon 0 times the charge enclosed. Right. The same way Coulomb's law also we learned the force between the 2 point charges, that is equal to 1 by 4 pi epsilon 0 q1 q2 divided by r square we learned. So here we can prove that we can derive Coulomb's law from Gauss law. How we will do that? So proof of or derive Coulomb's law from Gauss law. How we can derive the Coulomb's law from Gauss law? Okay, so from Gauss law we should prove, right? So I am considering a sphere which is having a point charge inside. I'm considering a small surface element ds over here, and electric field will be acting radially outwards. The surface charge ds surface integral will be acting normally outwards. Okay, so already as per Gauss law, closed integral E dot ds is equal to q by epsilon 0. Okay, for that what is E? E is equal to E into closed integral ds is equal to q by epsilon 0. So here we are going to find out E, right? E into 4 pi r square equals q by epsilon 0. Therefore E we will get it as 1 by 4 pi epsilon 0 q by r square. This is E. Okay, now I am considering a test charge. Suppose a test charge Q0 is, here I am considering this point as P is on P. Then F is equal to Q into E. Okay, Q0 into E. So this is equal to 1 by 4 pi epsilon 0 Q0 by R square. This is our Coulomb's law. Now we got it right. So this is how we will be deriving the Coulomb's law from Gauss law. Clear? So now we will do one or two numericals based on this. A total electric flux emanating from a closed surface enclosing an alpha particle. So electric flux, we get total electric flux emanating from an alpha particle. Alpha particle means we know it is He24. That is alpha particle. The number of charges will be 2. Two positive charges and 2 negative charges are there. Total flux linked with the circuit is equal to 1 by epsilon 0 times total charge enclosed in the surface. Right. So 1 by epsilon 0, 2 times the electric charge. Two electrons and two electrons and 2 protons are there. So 2e is the charge. So the total flux will be equal to 2e by epsilon 0. Clear? So the next one is S1 and S2 are two hollow concentric spheres enclosing charges Q3, Q respectively. Okay, what is the ratio of electric flux in S1 and S2? What would be the electric flux through S1? And if air S1 is inside the replaced by a medium of dielectric constant 3, what will be the electric flux in S1? So first I will draw the diagram which is given over here. This is, and here it is Q, and this is 3Q, S1 and S2. First we should find out what is the ratio of electric flux through S1 and S2. In S1, what is S1 electric field? S1 will be equal to Q is the charge enclosed in S1, right? So it is Q by epsilon 0. What will be the flux through S2? That is, what is the total charge enclosed in S2? 3Q is there, here Q also there. So what is the total charge enclosed in SQ? 4Q by epsilon 0. Right, now how we can find out the ratio of phi1 by phi2? Phi1 by phi2 will be equal to 1 by 4. Okay, clear? So this is how we will be finding out the total charge. So here in S2, Q also there, 3Q also there. But in the case of S1, this 3Q is outside charge, not inside the charge. So inside charges only we will consider in the case of Gauss law. So next one is, what is the ratio? What would be the electric flux through S1 if air is replaced by a medium of dielectric constant 3? Okay, so what will be the if it is replaced by this, if it is given a dielectric constant having 3, so what will be the flux in first one will be equal to total charge enclosed divided by epsilon 0 if it is vacuum. If medium is there means epsilon r epsilon 0. Epsilon r is given as 3, so we will get it as phi is equal to 3 epsilon 0. Okay, so if it is this, all these cases we are considering for vacuum. Okay, if medium is there inside, that medium value also we should include, that is Q by epsilon 0 epsilon r we will get phi is equal to. Okay, this is the formula. Clear? So I think these portions are clear for you, and if you like the channel, please don't forget to subscribe, and don't forget to write down the important formulas of each and every chapter, and you should revise in between. Okay, so thank you for watching. Bye.